In lesson 19, we're actually looking again at linear differential equations of higher order, but some concepts we're going to look at here are linear combinations and linear dependence and independence. Also the complementary solution y sub c, just the notation for that, and the particular solution y sub p of x, and the relationships with those. First of all, the concept of linear independence. Before you talk about linear independence, you really need to understand the concept of a linear combination, however. Pretty much a linear combination is anytime you take several functions times a constant each and add them together. That's a linear combination. A set of functions are said to be linearly independent if no function in here is a linear combination of the other two. The first one I can see is not going to be linearly independent. It's going to be linearly dependent because this third function is just 2 times this function minus 3 times this function. And so I can see that they're definitely not going to be linearly independent. Another way this is often written is if you have constants, I'll call it c1 times your first function plus c2 times your second function, and these have to be constants, c3 times your third function. If you have constants that set that equal to 0, then if they are truly linearly independent, every single one of these constants, c1, c2, and c3, would have to be 0. If there are any groups of constants other than all 0 constants that would make this equation true, then the set of functions given would be linearly dependent. Now in this case, like I said, if I let c1 be equal to -3, or let me make it +3, because I want it to cancel this one, and if I make c2 equal to -2, then I can just let c3 be equal to 1, and then this equation is going to be true. So I'll just say that combination works. So there's a group of non-zero constants that make that 0, therefore it's linearly dependent. And now the second set of functions, x squared, x cubed, e to the x, and e to the negative x. Well, just looking at it, I don't really see any way. I can't take any constant times x squared to give me x cubed. I can't take any constant times e to the x to give me e to the negative x, so it looks like they are going to be linearly independent. To kind of spell it out again, if I take c1 times x squared plus c2 times x cubed plus c3 times e to the x plus c4 times e to the negative x and set that equal to 0, or say that's equal to 0, then it must be the case that c1 equals c2 equals c3 equals c4 equals 0. There's no other constants, c1, c2, c3, or c4, that would set that entire equation equal to 0. And therefore they must be, I'll say this is all that works. Therefore they are linearly independent of each other. And what about the last crew here? Sine squared, cosine squared, and 5. Well, anytime you see sine squared and cosine squared together, you need to think of the trig identity sine squared plus cosine squared equals 1. With that in mind, I can see if I take 5 times this plus 5 times this, that's going to give me this one. So 5 is a linear combination of the first two. And so let me go ahead and rewrite the equation again from the definition. If I take c1 times the sine squared x plus c2 times the cosine squared x plus c3 times 5, and that's equal to 0, well, I can find non-zero constants that make this work. Namely, I could let c1 be equal to -5, c2 be equal to -5, and c3 be equal to 1. Then I'll have -5 sine squared minus 5 cosine squared, add that up, and that's -5, and then over here I have +5, that is 0, so that works. So this again would be an example of a set of functions that's linearly dependent. Next here it says a homogeneous linear differential equation of order n, and we talked about that in lesson 18, will have exactly in, and this is an important theorem here that states this, a homogeneous linear differential equation of order n will have n linearly independent solutions, the linear combination of which forms the general solution. So we don't have to just say an n-parameter family of solutions. We can say this is the general solution as long as we found all of the linearly independent functions that are solutions to it, and there are n of those. A non-homogeneous linear differential equation of order n will also have n linearly independent solutions for its associated homogeneous differential equation. And by associated homogeneous differential equation, all I mean is, like if you have a differential equation like this, this is not homogeneous because you have some function over here that's not 0. This differential equation's associated homogeneous differential equation would be this one up here, where the right-hand side is 0. Just replace the right-hand side with 0. That's the associated homogeneous differential equation. And so clearly that's going to have n linearly independent solutions again for the homogeneous, associated homogeneous one. And then again, the linear combination of which is known as the, in this case, it's called the complementary solution, because it's not the solution to the differential equation, it's the solution to the associated homogeneous differential equation, so it's known as the complementary solution. It complements your particular solution. And so by complementary, we use the notation y sub c of x, and that's what was given up above. That's the complementary solution. And then the blank solution, y sub p of x, this is the particular solution to your non-homogeneous differential equation. So like it says, it represents a function that is a solution to the given non-homogeneous linear differential equation, and y equals blank is also a solution of that non-homogeneous linear differential equation. Well, if y sub c of x makes that left-hand side equal to 0, then adding y sub c of x to y sub p of x still gives you another solution to your differential equation. So y sub p is the complementary solution, that's what makes that left-hand side 0, and y sub p is a particular solution that makes that left-hand side equal to your q of x, whatever it happens to be. So if I add 0 to q of x, I still get q of x. But this is what we're going to use to try to help identify the general solution down the road. And so example 2 is just illustrating these facts, applying them. First of all, it says show that y equals e to the 2x and y equals e to the negative x are solutions to this differential equation. And clearly they're linearly independent again. One is not a multiple of the other. And then it says, and use the above information to identify the general solution to this differential equation. Well, first of all, the fact that they are solutions to this, I will work out and post that in Angel. But as far as identifying the general solution, I'll go ahead and do that here. Kind of leave it as an exercise for you to prove that they are solutions, but the general solution is y equals a linear combination of, so I'll say c1 times e to the 2x, linear combination of the two independent solutions there. This is a second order linear differential equation, and we have two linearly independent solutions there. Therefore, the general solution is just a linear combination of those two. So it's a constant times one solution plus a constant times another. And then it says show that y equals cosine of x is the solution to this. Once again, I'll leave that as an exercise, and I'll work it out and post it in Angel. Then it says, and use the above, or use the answer to example 2 to identify another solution to this differential equation. Well, I know from up here that if I take the complementary solution plus the particular solution, that gives me another solution. So that's what I'm doing here. So another solution would be the complementary solution, which I just found in example 2, because that was the solution to the associated homogeneous differential equation. And then plus the particular solution, which is the cosine of x. This will also be a solution to that given differential equation. Because I know this piece right here, when I go through and take its second derivative minus its first minus 2 times the function, that's just going to return 0 from what I saw back here in example 2. So I've got 0 plus the cosine. So if cosine's a solution, 0 plus the cosine is also a solution. And that's it for lesson 19.